So, hello dear students, welcome again all of you. So, in this today's lecture, we will discuss about the neutron-proton scattering interaction, so which has been performed experimentally, so at low energies, and we will discuss the theoretical results, and then we will compare the calculations which have been derived experimentally. So, in the meantime, so mark your attendance. So okay, 10 people are connected with us. So let's start our lecture. Now the fact which we have studied from the deuteron problem, and we have derived that the deuteron, it is a bound system, and which shows that the attractive forces which exist between neutrons and protons. Now how we can study more about these type of nuclear forces? So in order to get further information about the internuclear forces, so what the scientists do, they try to interact these neutrons from outside, they try to interact the nucleons with the nucleus. So what they have studied, so they obtained a study of the scattering of free neutrons by protons which are present in the target. Now in such experiment, so what they have used, so they have done a parallel beam of neutron which is impinging on a target which is containing hydrogen atom. Now what type of target it should be? So it should be a water target, having target which contain water impurities, or a target which contain paraffin wax. So target composed of paraffin wax or water impurities. And what they have studied, they have studied the number of neutrons which are being deflected through various angles, and they have tried to determine the function of this neutron energy which are being scattered. So here I would like to mention why they considered neutrons. So since neutrons, so they have no charge, so therefore they are unaffected by the electrostatic field of force, and their scattering will directly reflect the operation of the nuclear forces only. So it will be unaffected with the Coulomb field which is present due to the protons which are present in the nucleus. So it is unaffected by the electromagnetic field, and then it becomes easy that the scattering it is happening only because of the nuclear interaction or due to the nuclear forces only. Now as I have explained in my previous lectures, so two kind of reactions, so they can be involved in this NP reaction experiment. So one is the scattering and other is the radiative capture. Now again the scattering, it can be either a elastic scattering or inelastic scattering, while the radiative capture, it has the low probability because of the low cross section area for the high energy neutrons. So we know that the radiative capture reaction, so cross section, so it is inversely proportional to 1 over V, and this is very less at a neutron which are moving with very high energy. Now second, they have considered these paraffin wax because the chemical binding energy of proton in these molecules is about 0.1 electron volt. So what does it mean? So we can easily scatter the protons from this bound system so easily. So if we strike a neutron which is having energy greater than this binding energy, then we can easily eject those protons which can be get scattered at different angles. So if we strike neutrons, so that is of energy which is greater than 1 electron volt, so it is easy to knock out proton from these molecules, and those protons, so they get free. So this is at a lower limit to the neutron energy. So what we have studied experimentally, that until the energy of the neutron it is less than 10 MeV, so only protons from S wave overlaps with the nuclear potential, so the protons from the S wave get scattered. So when we exceed the energy, then this 10 MeV, then the role of this angular momentum, it comes into dominant. So उस केस दे विच की है कि अदर the p orbital nucleons and the higher subshell nucleons, so they also get scattered. So in order to see the clear scattering of this protons which exist in this S subshell, so we generally strike the neutrons that is having energy less than 10 MeV. So the Schrodinger wave equation, so I will not go in detail about why we use this Schrodinger wave equation, because you all know the concept of the classical versus quantum concept. Because in the quantum concept, so which has been firstly explained in 1925 by the de Broglie. So de Broglie, he just say that, so the particle which is moving with some velocity having momentum p, so then it can have some sort of a wavelength, or it so it exists in some of a motion, so which exerts in the form of a wave. So he gave the concept of wave particle duality. So the particle, it can act as well as a wave as well as a particle. So based on the uncertainty principle, we can identify the relative momentum which is changing with respect to its position. So Schrodinger used this de Broglie equation. So in his differential equation which is used for the three-dimensional equation, so he derived the concept of energy, so which is quite similar with the Bohr energy spectrum. So later on he derived those four quantum number which can explain about, so the N, L, ML and MS. So these are all about the quantum concept, so that is at the atomic level or at the nuclear level, so that is at the microscopic level. So the quantum concept, it is dominant. So the Schrodinger equation for two-body problem, so this we can write del square psi plus m over h bar square E minus VR psi. So he gave the term, so which is quite helpful in order to identify the various parameters of the wave. So this is known as the wave function, and from the scale of this wave function, that is known as the probability, we can identify the existence of the particle at particular instant of time. So using this time independent Schrodinger wave equation, So he derived out the interaction of the incident neutron, and then he compared these interaction with respect to the scattered protons, so which are getting scattered at different angles. Now if we consider at large distances, so from scattering, so the solution of this equation, so it is something like exponential of ikz, so where z it is representing the distance, large distance, plus exponential of ikr over r into f theta. So this particular first portion, it is representing the incident wave solution, and this is second, it is representing the scattered wave solution. So we will solve these two wave solutions separately, and then from that we can find out the value of this important parameter which is known as f theta, that is generally known as the scattering amplitude. So which tells us how much portion of the protons which are being scattered, and using the spherical coordinates of this f theta we can calculate the value of this differential cross section, that is d sigma over d omega. So that is at a particular range of solid angle d omega, so that is f theta square. So from this scattering amplitude we can calculate the differential cross section, and from this differential cross section if we integrate it, and we can calculate the total scattering cross section. So this is our main motive in order to calculate the total scattering cross section. So what we have to calculate is, total scattering cross section for NP scattering interaction at low energies. So let us try to draw a diagram. So here we have incident neutrons, so which are moving with a velocity v. So having wave function, incident wave function, that is of the order of exponential of ikz. So this is our nucleus of a particular molecule of paraffin wax. So when this neutron they interact with this nucleus, so from that the proton they get scattered out, and these are the scattering spherical waves. So these are scattered spherical wave. So it is something like when you throw a stone in a still water, then you can observe that, so the spherical waves, so in the form of solitons, so they starts to move up to a particular distance. So it depends upon at which velocity you have thrown the stone in that still water. So similarly these protons they get scattered at different angles, and suppose this is the initial waves, and the protons so they get scattered at some particularly scattering amplitude. So this portion that represents the scattering amplitude of the wave. So if this is angle theta, that is the scattering of proton at angle theta, and this angle it represents d omega, that is our solid angle. So here we can keep the detectors in order to count the number of protons which are striking on the detector plate. So to compute the differential scattering cross section, so we must have the number of particles, that is dn, they are scattered in unit time by one target nucleus into a solid angle d omega. So this we have already discussed. So let the incident or the incoming flux of particles, so that is generally represented as f, that is the incident wave function multiplied by this v. So similarly you can write the outgoing wave flux. So outgoing flux, so that is equal to dn number, which is the flux of scattered particle. So what is this number? So it is equal to the flux of scattered particle multiplied by the area. So if this is up to a distance r, they can propagate, and the area will be equal to r square into d omega. So the total number of scattered particles, so that is equal to scattered flux of particle multiplied by cutout area of, that is r square into d omega. So this we can write as f theta square v into d omega. So from this outgoing flux, so we can calculate the differential cross section. So that is equal to d sigma, which is f theta square v into d omega into v. So that is f theta square into d omega. So once we find out the differential cross section, from that we can find out the total differential cross section by taking the integration of this f theta square into d omega. So since this is spherical scattered wave, so they can move up to an angle of from 0 to 360 degrees. So we can write it as integration of 0 to 2 pi as 2 pi sine theta into d theta, and this equation becomes f theta square into sine theta d theta. So once we find out the value of this scattering amplitude f theta, from that we can calculate the value of this total differential cross section. So let us do the derivation of this NP scattering in order to drive these relations, so which we generally known as the phase shift analysis of NP scattering. So in the absence of scattering, so when the particle it get free, so in that case the nuclear potential it becomes 0, then the value of this Schrodinger wave equation, so that is equal to 2m e over h bar square into psi, which is equal to 0. So when the proton it get free, so then Vr becomes 0. So this has a solution that is equal to e raised to power ikz. So this type of wave function it can be expanded. So let us say this is our equation number 1. So this type of wave function it can be expanded into a series in terms of spherical harmonic functions. So what we get is we get the wave solution. So for this spherical harmonic function of exponential of ikz, that is equal to ikr cos of theta, and this we can write as summation of L, which varies from 0 to infinity, and that is RL theta, that is our radial wave function, and psi L theta into phi, so that is our spherical wave function. So RL represents the radial wave function, the second YL theta, it represents the spherical harmonic function. So here L, that is the integer, it representing the number of partial waves. So L is representing the number of partial waves which are being scattered, and it signifies the orbital angular momentum of system. So let us say this is our equation number 2. So this RL theta, that is the radial wave function of this part. So the radial solution of this equation, it can be represented with as 1 over r square d over dr r square dr over dr plus m over h square e minus vr minus l plus 1 over r square into r, that is equal to 0. So this is the same equation which we have studied for the neutron problem. So that is the radial wave solution of a 2 nucleon system. So this equation, it has two solutions. So it has two solutions. So one is not, second is the finite solution at origin, and it can be represented in terms of spherical Bessel function. So we can represent the radial wave solution of the solution which is starting at origin, and the radial solution, it can be represented in terms of Bessel function, while the spherical harmonic solution, it can be represented in terms of Legendre polynomial. So the Bessel functional solution of our radial wave solution RL theta, so that is of the order of IL under root of 4 pi 2L plus 1 JL KR. So where JL KR, this is our Bessel function. So the scale of this wave, so it gives the dependence of probability density of the partial wave, so which has been explained in equation number 7. So this JL, that is the spherical Bessel function, so the asymptotic form of this spherical Bessel function, which is dependent upon the orbital angular momentum. So the asymptotic, I will not go in detail because these type of Bessel, Legendre polynomial. So you have already studied in your mathematical physics. So the asymptotic solution of the spherical Bessel function so JLKR, so that varies when R approaches from 0 to infinity, so that is equal to sine KR minus L pi by 2 over KR. So this we can write as sine KR minus L pi by 2. Let us open it. So it is 1 over 2i KR exponential of IKR minus L pi by 2 minus exponential of minus IKR minus L pi by 2. So the first few spherical Bessel functions, so for L is equal to 0, so our spherical Bessel function, so its value becomes sine KR over KR. So this is for the S wave scattering, and if we are considering the higher order partial wave harmonics, so for L is equal to 1, so that is for the P wave scattering. So Ji KR, so this Bessel function becomes sine KR over KR square minus cos of KR over KR. So similarly for higher order harmonics you can write down these values, but that is not of our interest because we need to have this value, that is for this S wave scattering. So similarly the spherical harmonic function, so that is in this equation, so our this second portion, so that is the spherical harmonic wave solution, so that we can represent in terms of Legendre polynomial. So our spherical harmonic solution, so that is 2L plus 1 under root over 4 pi under root PL cos of theta, where this PL cos of theta, that is our Legendre polynomial of order L. So the square of this spherical harmonic function, it gives us the angular dependence of the probability density of our nucleons. So the value of this Legendre polynomial for L is equal to 0, so that is equal to 1 for L wave scattering. So similarly for higher order harmonics, when L is 1, its value is cos of theta. When L is 2, its value is 1 over 2 3 cos square minus cos square theta minus 1. So but we are of this interest, that is for the S wave spherical harmonics. So we have break down our incident wave solution in terms of radial wave solution and the spherical harmonic solution. So let us try to write the incident wave solution. So the total wave function, that is the incident wave function plus the scattered wave function. So the incident wave function which we have represented, that is e raised to power ikz, which is of the order of e raised to power ikr cos of theta, while the scattered wave function, that is f theta exponential of ikr over R. So the total wave function we can write as exponential of IKR plus F theta exponential of IKR over R. So here the first term, it represents the plane wave which is traveling along the z-axis towards the scattering center, and the second term, it represents the outgoing scattered spherical wave. So this is our outgoing scattered spherical wave. So this is our incident spherical wave. So the factor f theta, that is generally the amplitude of the scattered wave in the direction of theta, so with respect to the incident beam. So again I have derived, we can find out the value of this scattering amplitude, and from that we can calculate the total differential cross section. So let us try to write or explain these waves separately. So the initial wave function, so for larger value of R from the scattering center, the radial wave function, it can be represented as two partial spherical waves. So one is the converging and the other is the diverging wave. So suppose this is our nucleus. So this is something like the incident wave, which is known as the converging wave. So when this get interacted with this target nuclei which is having proton, and after that we have this diverging waves. So let us try to write this incident wave solution, which is exponential of IKR cos of theta. So this we can write down as, so by putting the value of this Bessel function and Legendre function, so our this equation, it becomes 2L plus 1 I raised to power L over 2I KR into PL cos of theta, that is our Legendre function, and exponential of IKR minus L pi by 2 minus exponential of minus IKR minus L pi by 2. So that is our Bessel function. So this is the incident wave, which is representing the radial wave solution as well as the spherical harmonic solution. So each partial spherical wave, it is characterized by a definite angular momentum and its dependence on this PL cos of theta. So this is our incident wave solution. So let us say this is equation A. Now let us try to write the scattered wave solution or the final wave solution. So final wave function, or you can say scattered wave function. So the process of interaction, that is scattering, changes the relation between this converging and diverging spherical waves. So thus in scattering an additional factor is introduced. So in scattering wave function, an additional factor is introduced in the diverging spherical waves, because converge they interact ਕਨਵਰਜ ਦੇ ਉੱਤੇ ਦੇ ਕੋਈ ਚੇਂਜ ਹੋਏਗੀ ਨਹੀਂ, ਬਿਕੋਜ਼ ਉਹਨੇ ਹਾਲੇ ਤੱਕ ਪ੍ਰੋਟੋਨ ਦੇ ਨਾਲ ਇੰਟਰੈਕਸ਼ਨ ਕੀਤੀ ਨਹੀਂ। ਸੋ ਸਕੈਟਰਿੰਗ ਵੇਵ ਫੰਕਸ਼ਨ ਦੇ ਵਿੱਚ ਜਿਹੜਾ ਡਿਵਰਜਿੰਗ ਵੇਵ ਫੈਕਟਰ ਆ, ਸੋ ਦਿਸ ਇਜ਼ the factor which get changed, because now the wave have interacted with the protons or the neutron, they have interacted with the proton, and this diverging wave, so that get changed. So therefore how much it gets changed, so that is we represented with a additional factor, so that we generally represented as a coefficient of SL. So this is scattering coefficient. So therefore in the diverging wave section we will introduce this SL term. So we will introduce this coefficient in the diverging wave. Now if you look at this wave solution, so this first portion it is representing as the diverging wave. So I will write with different color. And this is known as the converging wave. So that is our total spherical wave solution. So this portion, that is the converging wave solution, and this first term, that is the diverging wave solution. So we will introduce a factor of SL in this diverging wave solution. So it becomes SL exponential of IKR minus L pi by 2 minus exponential of minus IKR minus L pi by 2. So rest all the terms, so they will be same. So for this SL, that is the scattering coefficient factor, so for elastic scattering, so there is no absorption of the wave, so therefore the value of this SL for elastic scattering, it is equal to 1 for elastic scattering, while the value of this SL, it is vary from 0 to 1, that is for inelastic scattering. So next, third factor which will also get introduced, because the converging and diverging waves, they are no longer the same waves, so there is a factor of SL that we generally represented as exponential of 2I into sigma L, where sigma L, that is known as phase shift, कि भाई इंटरेक्शन तो बाद जिहड़ी वेव दा फेज आ वो कितना चेंज हो गया है. So where sigma L is having real values, while this we can write as, in case of absorption, we write this scattering coefficient as eta L exponential of 2I into sigma L, where eta L is the amplitude of the nth diverging wave solution. So where eta L, that is the amplitude of nth diverging partial wave. So this phase shift, it is a very complicated function of energy, or it is a very complicated function in terms of wave factor, but at low energies for this short range nuclear interaction, so this phase shift, it can be written as K2L plus 1, where K is the wave vector, or you can write it as 1 over lambda 2L plus 1. And for S wave scattering, so for S wave L is equal to 0, so this phase shift, that is inversely proportional to 1 over lambda. So this we can represented either a positive phase shift or a negative phase shift. So let us say this is our nuclear potential. So suppose this is the value of minus V naughts up to a order of R naught. So wave gets scattered. So if it is getting inclined, suppose this is until the potential they are bound. So let us draw a demarcation. So this is the change in phase shift. So this is our original converging wave, and this is the final diverging wave. So change in phase shift, so that is of the order of this much. So this is the value of sigma L, that is change in phase shift, and because it is moving ahead as compared to the previous wave, so the phase shift is positive. So value of sigma L, it is positive, and if it is moving or it is lagging behind the original wave, so suppose this is our nuclear potential. So this is our original wave, so it is if it is moving behind, so here the wave is lagging, so this phase shift is repulsive phase shift, or you can say this is negative phase shift. So this is you can explain about the nature of phase shift, so whether it is a attractive potential or a repulsive potential. So the scattering cross section, how we can calculate? So from the scattering wave, so the psi scattered wave function, that is exponential of ikz plus f theta exponential of ikr over r, and from that you can calculate the scattered amplitude. So that is almost the same, but a SL coefficient, scattering coefficient, which is getting added in the diverging wave function. So 2L plus 1 over 2I KR, so where L varies from 0 to infinity, IL PL cos of theta. So the Bessel function now becomes SL exponential of IKR minus L pi by 2 minus exponential of minus I KR minus L pi by 2. So this is the scattered wave function. So here the diverging wave, it is being added with a scattering interaction factor SL. So this is our diverging wave, this is our converging wave. So from this we can write this equation as so 2L plus 1 I raised to power L over 2I KR PL cos of theta. So putting the value of SL, that is exponential of 2I sigma L into exponential of I KR minus L pi by 2 minus exponential of minus I KR minus L pi by 2. So if we introduce this phase shift within this exponential function, so this becomes I KR minus L pi by 2 plus 2 sigma L minus exponential of minus I KR minus L pi by 2. So using the trigonometric relations, because we know exponential of IKR minus exponential of minus IKR over 2I, that is equal to sine of KR. So this equation, that is exponential of IKR minus L pi by 2 minus exponential of IKR minus L pi by 2 over 2I. So this becomes sine of KR minus L pi by 2. So therefore at larger distances from the scattering center, the wave function practically retain its original form. So because when the wave, scattered wave, it is moving, and at the larger distances the scattered wave function, it retains its original form except the appearance of the change in phase shift. So due to the scattering interaction, so the wave function after scattering, so it can be written as psi L, that is the scattered wave function. So it can be directly almost same, but a change in value of sine KR minus L pi by 2 plus sigma L over KR into PL cos of theta. So thus the value for S wave scattering psi naught when L is equal to 0, so this is equal to sine of KR plus sigma naught over K, because this psi naught, no, that becomes U naught of R, because U naught R, that is equal to R into psi naught of R. So this is the radial wave solution of the scattered wave, so that is at larger distances. So the wave function for phase shift, so will be same. So the phase shift, it is having a value of minus pi by 2 sigma to plus pi by 2. So the scattering amplitude, so once we calculate the scattered wave solution, we calculate the incident wave solution, and from that we can calculate the scattering amplitude. So the scattering amplitude, so scattering amplitude, that is f of theta, so it will be equal to psi scattering wave function minus the incident wave function. So the value of f theta, because we also know this value, we also know this value, from that the scattering amplitude we can write that is of the order of 2l plus 1 exponential of 2I sigma l minus 1 over 2ik into pl cos of theta. So I hope you can easily derive these values because we have calculated the value of this psi scattered, and this is our psi scattered value, scattered wave function, and this is our incident wave function. So this is our incident wave function. So when you subtract these two equations, from that you can calculate the value of the scattering amplitude, and it comes out to be of the order of 2l plus 1 exponential of 2I sigma l minus 1 over 2ik pl cos of theta. So this equation exponential of 2I sigma l minus 1 over 2ik, so this we can write as, if we take exponential of I sigma l as constant, over 2ik, so this equation becomes I sigma l over k into sine of sigma l. So putting these values in this scattering amplitude, so our scattering amplitude, it becomes f theta, that is summation of 2l plus 1 exponential of I sigma l over k sine of sigma l into pl cos of theta. So once we find out the value of this scattering amplitude, from that we can calculate the differential cross section. So the differential cross section, as we already discussed, so its value is the square of this scattering amplitude magnitude, and it is summation of 2l plus 1 exponential of I sigma l over k sine of sigma l pl cos of theta square. So d sigma, that is f theta square into d omega, so d sigma, that is f theta square into d omega, so this becomes 2l plus 1 exponential of I sigma l over k sine sigma l pl cos of theta square into d omega, where d omega is the solid angle. So we can put down the values. So this d sigma, it becomes so from this we can calculate the total scattering cross section, that is d sigma theta into d omega, so that is in a range from 0 to 2 pi for double integration 0 to pi. So this we can write as 2 pi 0 to pi f theta square into 2 pi sine theta into d omega. So it comes out to be 2 pi over k square summation of 2l plus 1 exponential of I sigma L psi sigma L PL cos of theta square. So because of the orthogonality of the Legendre polynomial, so you can write down these values and it comes out to be so that is 2 over, so this values it comes out to be 2 over 2L plus 1, and this equation it becomes 2 pi over k square summation of 2L plus 1 square. So when we open this whole bracket, so that is sine square sigma L into 2 over 2L plus 1. So this becomes 4 pi over k square summation of 2L plus 1 into sine square sigma L, where sigma L is the change in phase shift. So for calculating these cross sections, so what is important? So it is important to know about the change in phase shift of the scattered wave. So for that particular partial wave solution. So this total scattering cross section, this we can also write as 4 pi lambda square summation of 2L plus 1 into sine square into sigma L. So similarly you can calculate this total scattering cross section for different partial waves. So for L is equal to 0, that is for S wave scattering. So the scattering amplitude F naught, that will be equal to exponential of I sigma naught over k into sine sigma naught. So this you can calculate from this equation which we have. When you put the value of this L is equal to 0 in this equation, so you can calculate the scattering amplitude for S wave scattering when L is 0. So this term becomes 0. So PL, that is Legendre polynomial, it is equal to 1 for S wave scattering. So this is the equation which we get. So this we can also write as 1 over k cot of sigma naught minus ik. So F naught, that is 1 over k cot of sigma naught minus ik. So similarly from this scattering amplitude for S wave you can calculate the total scattering cross section for S wave when L is equal to 0. So it comes out to be 4 pi lambda square over 1 plus cot square sigma naught, or you can also write it in terms of wave vector 4 pi k square 1 plus cot square sigma naught. So these are the standards solution of the total scattering cross section for a S wave scattering. So when a neutron it is interacting with a proton, so in NP scattering experiment. So the maximum cross section for S wave scattering so the maximum values it can be equal to 4 pi lambda square when there is the no change in phase shift. So the maximum value it is 4 pi over k square. But for L naught is equal to 0, that is for P wave or the higher order harmonics, higher harmonic waves. So the value of this total scattering cross section, that is 4 pi lambda square 2L plus 1 into sine square sigma L, and the maximum value for higher order harmonics, so that is equal to 4 pi lambda square 2L plus 1. So this is the expression of the scattering cross section for low energy particles, so when they are interacting with the proton targets. So these are the spherical symmetric solutions of partial waves of NP scattering experiments. So this is the end of the NP scattering derivation. So this is very important article, and generally it comes in the exams most of the time. So I hope you will understand and try to derive this expression, and if you have any doubt you can ask me personally or you can put your questions in the comment box. So from tomorrow onwards we will discuss the scattering length, what is its significance. We will discuss about the ortho and para hydrogen and how the scattering amplitude or how the scattering length it is different for different interactions. So in the meantime, so you can mark your attendance again. Please write your name and roll number again to mark your attendance. So others also mark. So okay dear students, see you in the next lecture. You can keep your questions if you have any in the comment box. So I will send the PDF copy of these annotations on your WhatsApp groups.